In this video, we're going to take a look at finding the second derivative of a relationship that's expressed implicitly. So it's an extension of implicit differentiation that we've already taken a look at. I'm going to start with problem number 2 because I think it's a little less messy than problem number 1. It's the same process. So to find the second derivative, which is what we're asked to do here for the following functions, find dy dx, which is the first derivative, and then we're to find the second derivative. So we'll start just like we did before with implicit differentiation. Again, I'm working problem number 2. So we start by finding the first derivative. The derivative of cosine is negative sine y. And remember, we said when we take the derivative of the y term with respect to x, we get a dy dx. The derivative of negative 3x is negative 3, and the derivative of 2 is 0. We're trying to solve for dy dx. So if we do that, we'll add 3 to both sides. And then we will divide both sides by negative sine y. And we can express that as negative 3 cosecant of y. So we have the first derivative of the function, and now our job is to find the second derivative. So we're taking the first derivative of the first derivative. When we do that, just to show you where this notation comes from, if we have dy dx, and what we're doing is we're finding the derivative of that, so we're taking the derivative with respect to x, just so you know where that notation, why it's written that way. Notice that we have d squared y over the quantity dx squared if you just multiply it straight across, and that's why the notation has the square on the d in the numerator and then the whole quantity in the denominator. But nonetheless, our job here is to find the second derivative. So, in finding the second derivative, d squared y over dx squared, just continuing this problem, I'm going to find the derivative of this piece. So I get the derivative of cosecant is negative, so that'll give me a positive 3 cosecant y cotangent y. And then I took the derivative with respect to x, so I have a dy dx left behind. So here's the only little added thing to finding the second derivative. Notice that my second derivative has a dy dx in it. So all I'm going to do is to go back and replace that dy dx with its equivalent, its first derivative. So when I rewrite that, I'll have second derivative equal to 3 cosecant y cotangent y, and then in place of the dy dx, I'm substituting the negative 3 cosecant y, which was from here because they are equivalent to each other. And so when I clean that up, I'll have negative 9 cosecant squared y cotangent y. So really the big deal there is you take the first derivative, once you get that, you take the second derivative of both sides, and then when you have that dy dx that you see right here, you just replace it with its first derivative equivalent, and that's pretty much all there is to it. All right, let's take a look at another problem. I'm going to go on to number 3, or it's actually number 1 on page 20. Again, we've been asked to find the second derivative, and in this case we've also been asked to write the equation for the tangent and the normal line to the curve at the given point. So let's find the first derivative. Taking the derivative of e to the 2y, I get 2e to the 2y dy dx. Taking the derivative of the second term, I'll get negative 8x. The derivative of the third term will give me negative 3 dy dx, and of course the derivative of 0 is 0. I'm going to move the 8x to the right-hand side. I'm going to factor out the dy dx in the terms over here, so I get 2e to the 2y minus 3 is equal to 8x. And again, I just added the 8x to the right-hand side and factored the dy dx out of the terms on the left-hand side. To get dy dx by itself, I will have 8x over 2e to the 2y minus 3. So that's my first derivative. Now I'm going to go and find the second derivative. So the second derivative, d squared y over dx squared. I'm going to need the quotient rule here, so I will have down, so I have 2e to the 2y minus 3. D up, the derivative of 8x is 8, minus up, e to the x, 8x I mean. D down, the derivative of 2e to the 2y is 4e to the 2y dy dx. Don't forget to leave your dy dx in the y term. So I did down d up minus up d down over down 2e to the 2y minus 3 squared. Okay, now in this particular problem, I don't necessarily, since I'm using this derivative, let's see, we were finding the lines tangent and normal to the curve. Those directions are not very clear because I don't know if they want us to write the equation of the tangent and normal lines to the original curve or to the first derivative. For now, we'll ignore that because writing the equation of a line, y minus y1 is equal to m times x minus x1. Regardless of which curve we are working with, all we're going to do is use the derivative to generate the slope for us. The last thing I'm going to need to do on this second derivative, though, is replace. Now, this is going to get a little bit messy because we're going to have a complex fraction. This is dy dx, so it's going to come over here. So I'll have d squared y over dx squared, and no, they're not always this messy. So I have 2e to the 2y minus 3. Why don't I go ahead and distribute that since I'm at that point. So if I distribute the 8, I'll have 16e to the 2y minus 24 minus 8x times 4e to the 2y. And let me change colors here. In place of dy dx, I'm substituting 8x over 2e to the 2y minus 3 because that is the first derivative that I substituted in place of dy dx. So there it is. There's the substitution over 2e to the 2y minus 3 quantity squared. I can probably clean that up just a little bit more. Since all of this in the second term is multiplication, this 8x will divide with this 8x. And so I will have 16e to the 2y minus 24 minus, I'm going to keep that in parentheses for now, 4e to the 2y over 2e to the 2y minus 3 over, 2e to the 2y minus 3 quantity squared. Now at this point I could find a numerator or common denominator in the numerator. I'll go ahead and do that. So in doing that, that would give me 16, I lost my pen here, 16e to the 2y minus 24 multiplied by 2e to the 2y minus 3 minus 4e to the 2y. And this is my numerator. It's all over 2e to the 2y minus 3, and that's over my big grand denominator of 2e to the 2y minus 3 squared. And then as a last step, I don't think I'm going to multiply that. I guess I could multiply that through. So if I multiply these two terms together, or these two together, I will get 32e to the 4y. That'll give me negative 48e to the 2y minus 2 times 24 will give me another negative 48e to the 2y. I'm just multiplying my two middle terms together. Let me check myself on that. Negative 48 e to the 2y. So that'll give me negative 96e to the 2y plus 72 minus 4e to the 2y over 2e to the 2y minus 3 quantity cubed. So notice I had this to the first power. When I multiply by the reciprocal, that will become to the quantity cubed. And then as a last step, I can combine the e to the 2y, so I have 32 e to the 4y. 96 and 4 minus would give me 100 e to the 2y plus 72 over 2e to the 2y minus 3 quantity cubed. So here's my second derivative. It kind of got a little bit messy there, but if you take your time and are careful, you can get through that. And again, not all the second derivatives are as messy as this one. Now remember again, this problem did say that we were supposed to write the equation of the tangent line and the normal line to the curve. I'm just not sure which curve. I assume they're talking about the original curve. Notice also that in this problem they gave me an x value of 1/2. So if I were going to write the equation of the tangent line, I would have to substitute my x to the 1/2 in here and go and find the y value, which would probably necessitate the use of a calculator. So I'm not too worried about that in this problem. I just really want to show you the process of finding the second derivative. And again, the key is when you get that, so right here, let's change colors here. When you get that dy dx term, which you often get in the first derivative, you just simply have to replace it with what the equivalent of dy dx is. All right, let's go through one more problem just so you can make sure you got the process. In number 2, on page 20, it says we're just to evaluate that one at x equal to 2. Let's go ahead and start the process of finding the second derivative here, even though it just says evaluate at x equal to 2. So the first derivative, for the first term, I'm going to need the product rule. So I'll have the first 3x squared times the derivative of the second, dy dx, plus the second, which is y, times the derivative of the first, which is 6x. And then the derivative of 6y would be 6 dy dx, and the derivative of 9 is 0. I'm going to make sure I did that right. So product rule first, deriv second, plus the second, which is y, times the derivative first. Okay, I'm going to factor out my dy dx on the left-hand side, and that leaves me with 3x squared plus 6xy. Oops, no it doesn't. So that leaves me with 3x squared, a little bit more eraser here, minus 6. And on the right-hand side, I'm going to subtract the 6xy, so I get negative 6xy. So dy dx is equal to negative 6xy over 3x squared minus 6. That's my first derivative. Second derivative, again, it's going to get a little algebraically messy, but that's okay. It's not the end of the world. Just may feel like it. So I'm going to use the quotient rule here. So the second derivative, d squared y over dx squared, is equal to down 3x squared minus 6. D up, I'm going to need the product rule again, so I have first derivative of the second plus the second, which is y, times the derivative of the first, so that gives me negative 6y. Down D up, minus up, negative 6xy. D down gives me 3 times 2 is 6x over down, down. Am I going to clean first, or am I going to substitute the dy dx? I think I'll go ahead and do a little bit of both. So now, in place of my dy dx, I'm going to substitute its equivalent. So I will have d squared y over dx squared is equal to 3x squared minus 6 times negative 6x. Okay, here comes my dy dx substitution, which is negative 6xy over 3x squared minus 6. And then I'll have minus or a plus 36x squared y. Just multiplied that together over 3x squared minus 6 squared. Okay, taking that up, that will give me 3x squared minus 6. Let me get this little fella out of the way. He doesn't want to move. There we go. All right. Let's see. Plus times positive 36x squared y over 3x squared minus 6 plus 36x squared y over 3x squared minus 6. Oh, that worked out better than I thought. The 3x squared minus 6 divides out with the 3x squared minus 6. And so that leaves me with a 36x squared y plus a 36x squared y, which is a 72x squared y over 3x squared minus 6, which is my second derivative if I didn't make any calculation error.